All right, good. So let's get started. Welcome, everyone. My name is Babak Saraje. I'll be your moderator today. Thank you for joining us in this Floquet Summer School that is hosted by the Virtual Science Forum. As you may know already, the Virtual Science Forum is an open, collaborative, and volunteer-run initiative. And the purpose of it is to facilitate online scientific seminars and events. And if you would like to learn more, I will be posting some links. You can visit the webpage. We can find information and resources about how to organize events and give presentations, for example, in our Speakers Corner. That is an ongoing self-invited seminar series. So all of our content is available on GitHub, on our webpage, and on our YouTube channel, and it's open. I would also like to take this time to thank institutional support that makes our work possible, especially the support from the Kavli Institute of Nanoscience at Delft. So today, we will have 3 lectures. Each lecture will have about 50 minutes for the lecture itself, and we allow for 10 minutes for questions. Of course, this might vary a little bit depending on how the questions go. If you have some quick questions during the lectures, you're welcome to ask them during the lectures. You can raise your hand and we will alert the speaker, and you can unmute yourself and do so. For longer questions, we ask you to defer those to the end to not interrupt the flow. Now, I would also like you to check the attendee guide if you haven't yet. I will post a link to that as well in the chat. So today, the first lecture is by Takashi Oka from the University of Tokyo and ISSP, and he will tell us about the basics of Floquet engineering of quantum materials. And Takashi, you can go ahead and share your screen.
So thank you very much. I'll share my screen. Okay, so hi everyone, and yeah, good morning or good evening or good night, good afternoon. Okay, so today it's really my great pleasure to have this chance to give this talk here. So I'm Takashi Oka. Let me see. Okay, so I guess you can see my pointer moving around. Yes.
Yes.
Okay, good. Okay, so today I'll talk about the really basics of Floquet engineering in quantum materials, with a focus on very simple lattice models and very simple ideas. You're very welcome to ask any questions during my talk. Okay, so actually, so let me first begin by saying that my background, okay, so the Floquet physics, it's really not just theory, but many experimental groups are studying these periodically driven systems. There are many different okay, so backgrounds. So many researchers with different backgrounds are working on Floquet engineering. For example, my background is electron system. So this is an animation created by Koichiro Tanaka in Kyoto University. You can see that there's this really nice animation where a laser, okay, so this laser will come into this material, and you can see inside this material, you can see these big balls and small blue dots. They're supposed to represent lattices and electrons. Okay, so in electronic systems, this Floquet engineering is now slowly becoming a realistic way to control quantum mechanically control the state of matter. Also, there are different fields like cold atoms, where it is even more easier to really control the states. Okay. So let me start with this slide. Okay, so actually in solid state physics, so electron systems, the idea of trying to control phase of matter is really a very important concept. And of course, initially many people have been doing this using equilibrium methods. For example, so I show you here 3 typical ways to control a material and induce a very special phases like superconductivity in a insulating material. One is to apply strain. Okay, so you can apply strain to some organic material and you can turn it into a superconductor. You can also dope the material, so put electrons or hole inside the material. And then, so this is a famous phase diagram of couplets. You can turn insulator into a D-wave superconductor. Also, in some materials, you can even apply magnetic field. Okay, so in this case, you'll break or change the superconducting state into a FFLO state, very exotic quantum state, before turning it into a normal metal. Okay, so these are typical quantum control in equilibrium. Then, okay.
Excuse
the
me,
next, okay.
Takashi, as Babak said that we can do short questions. What kind of equilibrium do you have in mind when you say quantum control in equilibrium? What kind of equilibrium do you have in mind?
What kind of equilibrium is typically, so since the material is large enough, we think that these are like in a more or less like a closed system. Okay, so they are cooled, they're coupled to phonon and so on. They are in a canonical distribution. So in that sense, it's a equilibrium thermal state.
Do you mean a thermal equilibrium?
Yes, thermal equilibrium here.
Right, thank you.
But okay, yeah, thank you very much.
But you can accomplish another kind of equilibrium.
Here, but my focus is to move away from equilibrium. So going to something like this, so a laser-induced phase transition, but still trying to, okay, so since this idea of pressure, doping, or magnetic field, these are like a very easy way for us to understand what's happening. Although usually, typically these dynamical systems which change in time are very difficult to understand. In some situations, we can still use a concept very similar to equilibrium systems to understand what's happening. So today I'll try to explain some related things. So like I'll talk about this dynamical, or maybe it's more correctly dynamic localization, which is something very similar to applying pressure or strain. In terms instead of doping, you can photo dope material. So you can, the laser will induce electrons or hole. And for magnetic field, you can introduce effective fields or synthetic fields to which really works like a magnetic field. Okay. Also in solid state physics, this kind of coupling between electrons and light or photons are becoming a very, very rich field. So there was a very nice review article in Nature this year by these guys. And okay, so this is a very nice picture with many examples where you can have, okay, so this axis is very special. One is the photon number, and this direction is the electron correlation. Then you can have the maybe the intensity or cavity. The Floquet engineering that I'm going to talk about is really one panel, which is down here, but it has a, yeah, it's really part of this rich phenomenon where this electron and photon coupling are very important. Also, okay, so another point is that, so if we're going to talk about crystals and electronic systems, typically in an experiment, what really happens is that you're going to use a pulse laser. So here I have this like a schematic picture where I have, okay, so this red line is something like a pulse laser, and this line, solid line, it's supposed to represent the dynamics or the state of matter, which is excited by this laser pulse. And when you apply this pulse, the system will be strongly, coherently excited by the laser, and you will get this Floquet state, where many interesting phenomena such as band renormalization or electric field or this kind of Floquet engineering will take place. But we also have to remember that this is just the beginning of the story. In the real crystal, once so there's very strong laser pulse is gone, still there's other interesting effects such as some corrective motion, like magnetization or density wave, or some change in the chirality will take place before the system will slowly relax due to the coupling to the phonons. Okay, so here I have many review articles. Okay, let me, okay, so since this is Zoom, okay, let me, I can, I'll try to copy and paste this information to the chat corner so that you can have a look. Okay, so here. So here in the chat, I've now copied and pasted this what I've put in this PowerPoint. So there are already several nice review articles on Floquet engineering. The first one is by Andre Eckhart, who have been working on Floquet engineering in cold atomic systems. The second one is actually ours, and then Mark's very nice review and so on. The review article down here are actually not really about Floquet engineering, but something related to nonlinear optics in solid states. Okay, so with this, okay, so this was the introduction. Let me slowly move toward this idea of Floquet states. So I want to first illustrate or show you Floquet states, the examples of Floquet states. Actually, there are many, many examples out there. Some are even in YouTube. So, okay, so maybe this is a, maybe you already know this. This is the so-called Kapitsa pendulum. So in this example, if you strongly oscillate this axis or this center of the pendulum, you see that there's a stability point up there, which was initially unstable, but now you can see that it's really stable. And even if you perturb this pendulum around this point, it still recovers its position. So it's really, although it's globally unstable, it's locally stable. So you get such inverted state as a. So this is an example of a classical Floquet state. Okay, then another very famous Floquet state in quantum system is this phenomenon known as dynamic localization. This was first studied by Dunlop and Kenkre in the 80s. It's really a very simple system. It's just a one-dimensional lattice model coupled to a AC electric field. So you can see, so this is the Hamiltonian, and so this C diagram C. So this is the creation and annihilation operators. Okay, it can be fermion or boson, it doesn't really matter. It's really just a non-interacting system. And then, so this time-dependent phase term in front of this hopping from I to I plus 1. So this term, okay, so A times cosine omega t. Cosine omega t will oscillate, and A is the amplitude, and the theta is a step function. So it's going to be 0 before the time is, when time is negative, it's 0, and when time becomes positive, it's sharply turns on. Okay, here I'm going to show you an animation where I put one electron in this lattice system at the center. And the time, so here I have a number, it's from -5. And okay, so after putting one electron here, you can see that this electron is spreading out initially, but then when time becomes positive, where I introduce this oscillating field, then you can see that this electrons or this wave function suddenly stops. Okay, let me show it again. So initially it's spreading out, but after time t equals 0, the motion freezes. So in this sense, it's a localization phenomena. I'll explain why this happens after a few slides, but this is really a very simple example of a Floquet state. Okay, so this example, okay, so as an electron system, it's really like a one-dimensional lattice electron coupled to an AC field, so a laser field, moving positive and negative in this one-dimensional direction. Okay, but then if I consider a very simple generalization of that and have a two-dimensional lattice, so instead of a 1D, if I have a two-dimensional lattice like a honeycomb lattice, and then if I apply circular polarizer, so my laser field is now within this two-dimensional, so yeah, it's X and Y, but this field is now going to rotate within this XY plane, then the dynamics will have a very peculiar, will show a peculiar behavior. So I'm putting one electron at the edge, and you can see that this electron will move, basically move around the edge like this. Yeah, some part of the electrons will move inside the bulk, but the majority is going around the edge. And when it hits the bound, this edge of the edge, or here, this point, you can see that basically it's going to, so it's not going to reflect back, but it's going to move in the same direction. So it's really like a chiral edge state, or edge state in a quantum Hall system. So this phenomena is now known as an example of a Floquet topological insulator, where we discovered maybe more than 10 years ago. Okay, so so that was a theoretical thing, but animation. But there are very beautiful animations. Actually, it's already almost 10 years old, but in the group of New Gedik in MIT, I got this animation, which I'll show now, from Fahad here. So this is again an animation. So what am I showing here? So this is a surface Dirac cone in a three-dimensional topological insulator. So you might know that in a three-dimensional topological insulator, at the surface, there's a two-dimensional Dirac cone. And if you, okay, so you can see the Hamiltonian here. The sigma is the Pauli matrix, and P is the momentum. You have Px and Py, and this A is the electric field, so the gauge field corresponding to the electric field, which where the laser is now a circular polarized laser. A very interesting thing is that, okay, so if I look back again, so first you can see this like something like a wine bottle. Make this like this. So this is this looks like a wine bottle. Actually, this is the okay. So this is the energy, and this is momentum, and the Fermi energy is around here. So the electrons are occupying the states below the Fermi energy. So the states are down here, are fully occupied. And up here, there's states, but those are not occupied. And so using this time-resolved RPS, which is a very fantastic method, they can shoot animation or really like a movie where you apply circular polarized light and see how the occupation will change in time. Okay, so now if I move, you can see that the initial band, in addition to the initial band, you get some side bands. Okay, maybe it was difficult to see, but here, this is the slice of the same thing. It's a slice. And now this something like an X, this is the Dirac cone, the slice of a two-dimensional Dirac cone. And so up here, okay, so you don't, okay, if I like it evolve, you see this additional states up here and even here. So here, 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 and so on. So these are very, very beautiful movie. Okay, so today, I'll try to explain how to understand these Floquet bands. So these are known. So the states here are known as the Floquet bands. Okay. Oh yeah. Also, there's a very nice experimental work by McIver's with Cavaretti group. So they studied this laser-induced Hall effect in graphene. So they studied so here they have graphene, and they're applying a static voltage in one direction. But then once they apply this circular polarized light on this graphene, so you can turn this graphene into a quantum Hall state. So this state will turn into a quantum Hall state. And since they are all already applying this static voltage in this direction, having a quantum Hall state, they can induce a current which goes perpendicular to this direction. And they can see this in this is really a beautiful experiment where they see this current, and the time scale is like picosecond. If you're not really familiar with these numbers, pico means 10 to the minus 12. So it's really ultra fast. So this happens during the duration of this circular polarized laser. Okay. Okay, so next I will now move to the theory part. So I'll try to explain step by step the ideas of Floquet theory. I'll try to make it very, very simple because it is really simple. Okay, so first of all, the basic requirement is very simple. So you require that your Hamiltonian is periodic in time. Basically, this is the only requirement. So I have this capital T. This is the periodicity of the drive. Okay, so then the very important idea in Floquet theory is that you have to separate the dynamics into slow and fast dynamics. Again, I'll show you this animation from YouTube. Okay, so this is so probably you know what this is. This is a helicopter, and so somehow it's kind of strange. So this rotor is doesn't seem to be moving. That's really because the frame rate of this movie is synchronized with this rotation of this rotor. Okay, so then from this observation, okay, so actually you really know that actually this rotor is really moving around. But then if I just look into this motion where I have this stroboscopic motion, okay, so the slow dynamics that we see here are called stroboscopic motion. It's a motion where my time t is an integer multiple of this capital T. The capital T is the periodicity of the system. So 0, t, 2t, and so on. Within this very slow motion, or this stroboscopic motion, you can see that the system can acquire very strange dynamics. Here, you can see that this helicopter is floating in air. We know that this rotation of the rotor is introducing this force that is pushing up the helicopter. So such kind of effective force will show up. We can, scientifically or theoretically, we can understand such kind of effect through the so-called effective Floquet Hamiltonian, which I will explain in a few slides. So the keyword here is stroboscopic motion and effective Floquet Hamiltonian. Then, okay, so then there's this very fast motion. So this rotation. This rotation is called micromotion. So this is a time periodic fast motion which takes place within this one periodicity. So from 0 to capital T, there's a very fast motion. And the state corresponding to that fast motion is known as the Floquet state. Actually, this kind of separation of, okay, so here it was a separation of dynamics, but we know something very similar in solid state physics, which is this how the electronic wave function will behave inside a crystal. So there's an idea or concept known as the Bloch state in a crystal. So here, this is the real space image where I have a crystal. So let's say that this is the unit cell of a crystal. That I might have some wave functions like valence band and conduction band. Maybe its center is a little bit shifted like this picture within this unit cell. But then this structure will repeat itself when you go to the next unit cell. So this kind of periodic wave function is known as the Bloch state. And this is the position space. In the momentum space, we have this kind of band structure where we have this band of valence band and the dispersion of the conduction band. And we also know that so if we have a crystal, the low energy dynamics or the motion of the electrons in the crystal, which propagates to far away, is governed by this kind of band structure within this Brillouin zone. Actually, this kind of that dispersion within this Brillouin zone, this has a similarity with this stroboscopic motion in the Floquet system. Okay. So the micromotion corresponds to this kind of structure, which is periodic in space here in the Brooks theorem. And this stroboscopic motion or long time behavior is related to this dispersion. Okay, let me explain this a little bit more mathematically using the simplest possible example, which is this zero-dimensional or really just quantum mechanics that we learn in the first course in undergrad. So we can consider a differential equation. Okay, so this is a Schrödinger equation, but let's say that my psi is just a complex function. So there's no matrix structure. It's really just a number, complex number. And this H, okay, so this is the Hamiltonian, but since I don't have any matrix, this psi is just a number, a function. This H is just a real number. But the condition is that this real number depends on time, but it has periodicity. So when T, if we add this capital T, it turns into the same value. Okay, then, okay, so I'm trying to explain the idea of Floquet theory. It's very simple example. Okay, so to do this, let us write down the formal solution of the Schrödinger equation, which we know very well. So we can solve this Schrödinger equation easily. And basically, okay, so the wave function at time t is given by the multiple of the product of the wave function at the initial time, so t equals 0, times this phase factor, where I have this integral of this Hamiltonian. Okay, so this, yeah, we know about this. But then, okay, so in the second line, I will make a very weird change, modification. Okay, so I'm not doing anything spectacular. I'm just adding one term here and subtracting the same phase term here. So you see that this, I'm adding I times epsilon times t and subtracting I times epsilon times t, the same thing. But if I select this epsilon in a very nice way, which is that if I select epsilon to be the time average of my time dependent h, so this function h, which is something like energy or Hamiltonian, then then this term, so this first term, if I call this combination v of t, a function v of t, it has, so this v of t, it has a property that it becomes periodic in time. Yeah, it's really because, okay, so I'm choosing this epsilon to be the time average. So when this small t becomes capital T, the time periodicity, then this term and this term will cancel each other. So they will just become 0. And this v of t will actually become 1. Every time this small t will become the integer multiple of capital T. So in this way, we can see that so this term is periodic in time. Then the remaining term, so this guy that I have here, maybe I can call this exponential of minus I of hf of t. And yeah, so this hf, where here it's really just simply the time average of this Hamiltonian is the effective Floquet Hamiltonian. So just by doing this very simple separation, I separated my solution into the micromotion, so this very fast oscillating term, and to this phase term, which is not periodic in time, but slowly changes. Okay, maybe it's not slow. Okay, it's so this is not periodic in time, but it behaves as if it's really like a usual quantum, usual static system. So this structure is really similar to the situation where the Hamiltonian was a constant of time. Okay, actually, with this very simple example, I can already explain the physics of the dynamic localization that I showed you previously. So this one-dimensional lattice model that we have, if we consider this in a ring, so if I have a periodicity in the position space, then I can use, I can move the momentum space. Then for each momentum k, my for each momentum k, my Hamiltonian is something like this. So you can see that this is for each independent momentum k, this term is really just a number, real number, which is periodic in time. So in this example, so this guy will become my Hamiltonian for each momentum k, and the effective Floquet Hamiltonian correspond to the time average of this term. So here it's kind of very interesting. I have cosine and cosine omega t. So a cosine omega t inside a cosine. Actually, this kind of function, if you integrate it, it is known to be the definition of the known to be the zeroth order Bessel function. So basically, you obtain this Bessel zeroth order Bessel function times some factor and the cosine k. Then here I plot the zeroth order Bessel function as a function of a, and you can see that it's initially it starts from 1, but then it drops like this and oscillates, and here it will hit 0. So that's the point, exactly the point where I selected my A to B. So actually in this simulation, my A was really at 2.41 something. You can also see now that we know it, there's still some remaining oscillations. So the long time behavior, as a long time behavior, it's not moving. The wave function is no longer moving once it's positive, but still there's small vibrations. So this small vibration is the micromotion. And the long time behavior that's spreading out is this stroboscopic dynamics, which is now localized. Okay, now that was the simplest example without any matrix structure. Then let me make it a little bit more complicated by relaxing the assumption that this Hamiltonian had no matrix structure. But now, now let's say that my Hamiltonian can become a matrix or become an operator. Then, again, we know the formal solution of the time evolution, which we can write like this. This is the formal solution of the time evolution. And again, in a very similar way, I can rewrite this time evolution operator and separate it into v of t times exponential of minus I hf of t. So this h of, so actually what's really happening here is that I'm defining this hf using the relation that the exponential of minus I of hf of capital T should be this one-step time evolution. So u of capital T. Okay, so this is defining my hf. So let me move a little bit back. It's really the same thing that I was doing here. Here in this simplest example, I was defining my HF as a time average of this H here. Okay, so now everything is matrix and the non-commuting. I have to use this operator like expression, and I define my HF through this one-step time evolution. And then, so this was the definition of HF. But then this relation will now define my V of t, which is now my micromotion V of t. So this is the how we obtain the decomposition of a time evolution operator into this stroboscopic motion and micromotion. And this really sounds may sound very formal, but it really works. Okay, let me give so there are other realizations of having this kind of Floquet dynamics. So here, okay, so in this here, I was considering a system described by a Hamiltonian dynamics. Actually, there are some systems which sometimes there are systems where you don't really need any Hamiltonian, but you can just have like a time evolution operators. So maybe you can have the initial time evolution like u of 2 and u of 1, and then you can repeat it again and again. In this situation, the one periodicity, the periodicity will be time evolution generated by 2 of this. So u2 and u1 will generate time evolution, and you can repeatedly apply this to your states. So in this case, your Floquet state will be given by the product. Your stroboscopic motion is given by the product of these two unitaries. This kind of realization takes place in quantum walks or repeated quench and so on. And people often call this kind of construction the band time evolution. So 1 and 2 bands. Okay. So then let me with this background, let me claim or tell what's the aim of Floquet engineering. So please remember this movie of the helicopter. So we always want to, okay, so we can start from a trivial system, so something that's not moving. But then we want to apply some periodic external force, like this rotation. You can represent that as a perturbation, like h of t. And let's say that this is periodic in time. But then at the end, you want to realize something interesting. So you want to realize something, a state that has an interesting long time dynamics like h of f, or interesting dynamics in the u of t, so one step evolution, that's also interesting. And even this micromotion, that's another interesting thing. So the idea of Floquet engineering is to imagine or try to realize a state with interesting dynamics from a relatively trivial state by applying or designing this perturbation. So yeah, one example which I will focus today or maybe also tomorrow is this example where we have this honeycomb lattice and circular porous laser. And actually, you can show that this effective Floquet Hamiltonian of graphene plus circular porous laser is under some approximation really very similar to the very famous model of quantum Hall effect proposed by Haldane in the 80s. Okay, but we also still need to develop several tricks or mathematical ways. So one is to, okay, so we need to find a way to obtain the Floquet states theoretically. And for this, I will explain how to do this using the Floquet space-time picture. Then we need to find a simple way to construct or calculate this effective Hamiltonian. And this 1 over omega expansion or high frequency expansion is one way to do this. Okay, maybe. Okay, let me explain this formal part, and I will accept the questions. Okay, so this Floquet space-time picture. This was okay. So this applies for one-body system, so non-interacting systems, and the idea is really very simple, but the picture is really kind of rich, I might say. So we are now interested in a time-dependent problem. So we have a time-dependent Schrödinger equation. But then we move to this, move to the Floquet states. Okay, so here, let's say that our solution to the Schrödinger equation, psi, is given by a product of phi and the phase term. This phi is known as the Floquet state. This Floquet state is really like a very similar to the Bloch state in space. And this epsilon is known as the Floquet quasi-energy. So Floquet quasi-energy. So if we make this decomposition of the solution into the Floquet state and this phase term, actually this decomposition of the state into this phase and periodic Floquet state, this is equivalent to the decomposition I explained here. So the time evolution into V and this term. Actually, if you write these operators into solutions, states, it really transforms into this kind of decomposition. Okay. And but anyway, so we have this kind of decomposition. If we substitute this into the time-dependent Schrödinger equation, we can write the Schrödinger equation into an eigenvalue program. So this is a very important point. So we can write phi, and alpha is the index of the eigenstates, and this Hamiltonian H. Basically, this is just the original time-dependent Hamiltonian minus the time derivative with I. But the point is that now we have a very nice eigenvalue problem, which we can solve or using the usual matrix diagonalization. We can go one step further. So to have this space-time picture, we can go one step further and rewrite this or decompose this into Fourier modes. So let's say that my state phi, I decompose it into Fourier modes where my m, this will run from minus infinite to plus infinite, and this omega is the 2 pi over t, which is the frequency. This is just a discrete Fourier expansion, and my eigenvalue problem will look like something like a matrix diagonalization problem. But now this matrix has this index of the Fourier component. So M and N is the Fourier component, but this H of Mn, this is basically the Fourier transform of the original Hamiltonian plus this term, which is M times omega times identity. The origin of this term is this time derivative here. And physically, this corresponds to the absorption process of M photons. So it will give replica back in the spectrum. So if I write this Hamiltonian into like using this kind of big matrix where my diagonal components are H naught, here H naught and H naught minus omega, minus 2 omega, plus omega and plus 2 omega, and so on. And the off-diagonal terms, H of 1, H1, and H minus 1 down here. Actually, there will be H2 plus 2 and plus 3 and so on. But you can see this structure. So I have this big matrix, which I apply onto this big vector. The vector, so these vectors correspond to the Fourier mode of a time-dependent wave function or state. So this, sorry. So I can view this kind of system as a system which lives in a lattice system, which for a layered material in an artificial dimension. So it's schematically shown like this. So this side is what we originally have. So then let's study a two-dimensional material under a periodic drive, like this. But then, so this kind of problem mathematically becomes equivalent to a system where I have a layered material. So I have a layer of this, layer like this, and within this layer, the system is governed by H naught. So this H naught governs the original two-dimensional. If I have graphene, this is an original two-dimensional system. But then my H1 and H minus 1, this will connect the different layers, this layer, or in this way. Also, another, so we have this Fourier index M, you can consider it as a lattice index in this artificial direction. Also, another interesting point is that in this new direction, in this Fourier direction, we have a static electric field where the size field is given by omega. That's really because, so this term, omega, so 0, omega, 2 omega, and so on, or you can go trace it back to here, m times omega, this act something like tilted potential. So if you move in the omega direction, the energy is shifted by, if you move in the m direction, the energy is shifted by omega. So you're having a static electric field in this direction. Okay. So then, maybe the time is up, so I will explain this effective Hamiltonian tomorrow. But basically, the Floquet Hamiltonian that I have been showing is trying to take into account the effect of the other layers and projecting its effect to the states within the original layer. And there's a theory to construct this Floquet effective Hamiltonian. Okay, so with this, I want to end today's lecture, and I'm happy to accept questions.
Thank you. Very interesting videos also. Helicopter is pretty good. Hadn't seen it before. So there were some questions in the chat, a couple of questions there that I can bring up.
Yes.
And we'll see if people are there to pose them themselves. Nancy Sandler, do you want to bring your question up?
Yeah, hi. Thank you for a fantastic introduction. I am here with a student of mine, and you are really saving my job and my time, making it much easier. So I had one question. In fact, I have two if I have the chance. One has to do with your example of creating this topological Floquet state. And you show the animation with a wave packet located, placed at the boundary of the sample. And that becomes a chiral state, and that's where we see clearly the topology. I was wondering what would happen if you have your wave packet centered in the bulk, where there is practically no overlap with the chiral state.
Oh yeah, then in that case, it will basically spread out from the original point outward. And this, so basically you have a gapped Dirac cone as an effective model within the bulk. So the time evolution, this slow evolution. Okay, so what we are seeing here is really a slow evolution or stroboscopic dynamics. It really also has this microscopic motion, but you don't see it. And for this example of honeycomb lattice with circular polarized light, the effective Floquet Hamiltonian is given by a gapped Dirac cone. So if you start from the bulk, this delta function will spread out according to a gap Dirac cone.
Okay, can I have a second question?
Okay. Yep.
Just so this is for the last part of your talk. You referred to this when you show the Fourier transform for your generalized Floquet Hamiltonian. You automatically mentioned that this omega was associated with a photon, absorption or emission of photons. However, this is not necessarily always the case, right? Because I can imagine a mechanical motion when there is no electric field associated with it. And we will also have this term, right? So photons in a more generalized, could be a phonon, right?
It could be, yeah. It's not even now. Okay, so usually you use this photon, so when it's quantized, but it's not even quantized. It's really classical coherent vibration. So for a mechanical system, it is your vibration that's occurring, and this frequency omega is given by that vibration frequency. So I use this name photons just because I have this background of electrons in a laser, but if you have a different background, you can use a different name.
Yeah, I just wanted for you to make that comment. Yes. So thank you very, very much.
Yeah, thank you very much.
Okay. There was another question, a couple more questions in the chat, but maybe we'll go back and forth. So maybe take one question from people with their hands up. Fabio.
Thank you for the space. Takashi, thank you. Nice talk. Good presentation. Look, when you showed that slide, when you do the correspondence between Floquet states and the Haldane model. As far as I could understand, in the major part of your exposition, you talked about the problem of one electron, right? Even though in the problem of the 1D lattice. Here.
Yeah, here, yes.
Here in this slide, you have n electrons. But when you separate the micromotion from the stroboscopic motion in that mapping, how can we do it with many electrons?
So then you have to, okay, so this is a non-interacting system. So the solution is given by the Slater determinant. So basically, you can start from, okay, so if you have many momentum, and if your initial state, yeah, you have to construct your initial state first using the Slater determinant. And for each of the modes, basically it will just, time evolve. So since it's a non-interacting system, for each mode, you just solve this equation for each momentum k. And you can just, all the contribution will just be given by adding up the contribution for separate modes in a fermionic system.
Can I do one question? Because when you raised this answer, I could understand what you mean by non-interacting system. And as you can separate the micromotion from the stroboscopic motion. And in your animation, you showed the vibrations which remain in the end in the close of the package, right? When you did the correspondence between the Floquet states and the Haldane quantum model, in the Haldane quantum model, it also is a non-interacting fermion system, although it exhibits topological aspects, right? Here in this one. So in this state, we can also separate the stroboscopic motion and the microscopic motion, right?
Yes.
But during your answer, you showed me that a central point is that the system must be a non-interacting one. In other words, if I have an interacting system, I also can separate the microscopic motion and the stroboscopic one. If so, how can I do it when I do the evolution?
So
the time evolution.
Okay, so for a real interacting system, this is Floquet physics, so periodic driving. If you have a closed but interacting system, it is believed that you get heating. So since you're injecting energy by your external field, the system will heat up forever. And I think it is believed that the Floquet states, so these states phi that we have here, if the system is really a many body system, like a Haber model or something like that, this state will be like a trivial infinite temperature featureless state.
Right. Thank you.
So I'm going to jump in because we are running out of time. I know there are a couple more questions and there is some in the chat. If you post your questions in the chat, we can keep those and answer them later on. But now we are sort of a little bit into the time for Mark's lecture. So thank you, Takashi, again.
Thank you very much.
And the second part will be tomorrow.